We're going to introduce today's speaker. So like I said, today's the last session. It's going to be a little bit special of a session because it's going to be a double session from Harita and Matias on applications of post-Bayesian methods. I've been looking forward to this talk. I'm a big fan of both of their works, so um, I'm looking forward to hearing about their applications. So please take it away. I think Matias will be starting us off.
Yes, let me just share the screen. Cool, can you see it? Can you see my screen? Cool. Should.
Yeah.
Give me one sec, I think. Sorry. Some people. Okay. Great. So yeah, thanks for having me. It's nice to be on the other side. I'm presenting here. I'll present my work that I've done during my PhD. That's been supervised by Jeremias Anoblauch and FX Real, and I titled Post-Bayesian Inference for Robust and Conjugate Models. So a short outline. So basically, just starting with what I mean by Bayesian conjugate models and the benefits and the problems. Then I'll introduce the thing that I kind of like been working, which is like a weighted score matching base. And then finally, I'll talk about how we can extend that to regression, in particular Gaussian processes. So just to set the floor, I think I'm pretty sure here everyone kind of know this, but in Bayesian inference, we have some data generated from some true data generated process P, and we update our belief of a parameter interval theta that index a statistical model P theta. And we compute a posterior, which basically we update the belief of a prior given some or model. So these kind of have a bunch of different benefits like optimal update, uncertainty quantification, and inclusion of expert assessments. So in order to obtain that, we kind of assume the our model is correct. So there's 6 theta stars such that p theta star is equal to p. And we are able to compute this posterior in some way or another. So what I mean with Bayesian methods or conjugate Bayesian method is that there's like a huge family of methods that relies a lot on having this posterior available in closed form. Here I have 3 examples, and this is the one that I kind of focus, but there are many more. And this here we have a Kalman filter, which is basically trying to tracking a path, Bayesian online changepoint detections, and Gaussian processes. And they're all work really well, and they are super popular. So what do these Bayesian methods have in common is that basically these are either sequential Bayesian updates, which require closed form. So overall, these 3 methods require, or people really like the ability to have these posteriors in closed form. So in order to achieve this, the model choice is quite restricted. It's either Gaussian or exponential family, and that's it, which leads to a lack of flexibility to deal with extreme observations or outliers. So here we have the same exact example as before, but now where we add some outliers in the data set. So before the method worked really well, but now that we have outliers and have extreme observation, they are starting to struggle to follow the data. This is because basically these 3 methods are assuming the model is Gaussian, which is just breaking the assumption. So as I said, like this is breaking the assumption because basically here we are in this trade-off between being misspecified to model, having like a model that leads to a closed form posterior, or try to make like a more complicated model to model these outliers, but then we are not able to compute the posterior. And in those cases, we are not in the benefits of Bayesian inference anymore, and then it's kind of like we're breaking our assumptions. So the solution that is not surprise for anyone here in the seminar is that basically using generalized Bayes or like a post-Bayesian inference scheme, we can obtain the best of both worlds. Try to get a posterior that is robust to outliers, but at the same time being able to compute this in closed form. So that's basically the main question, is like how to select the loss function to obtain robustness and at the same time tractability. Just a quick reminder, the gen-based posterior replaced the likelihood by an exponential of minus some loss function. Now we update our belief, not by the likelihood, but by our loss function. And what kind of loss function that we can choose and select? Basically, the type of loss function that are super popular are divergence-based loss functions. And why they're popular and are kind of a good option, it's basically because a divergence, it's kind of a metric. It's not a metric, but it's like a measure between distance, measure of distance between two probability distributions, P and P naught, where P is the true delta generating process. And basically, this divergence is 0 if and only if these two measures are equal. So if we use a loss function that can approximate this divergence, basically it will minimize when we find a theta star such that it's really close to B. And in the case that our model is well specified, this will be the case when they're all always the same. But if not, hopefully we'll concentrate to a different one. And as David already said, under really mild condition, usually this posterior will concentrate to the minimizer of this loss, which hopefully will be more robust. So the divergence that we select and we have been exploring is generalization of score matching, which is like a weighted version of it. Score matching has been used for a long time for parameter estimation, hypothesis testing, and more recently diffusion models. This is why kind of like score matching has been super popular in the past years. And one cool thing about score matching is that they really work super well with unnormalized model, which I meant by that is that basically when you have a likelihood that you can calculate at f theta, but you don't know the normalizing constant. So this kind of method, the score matching works really well with this, and I'll explain why. So score matching or weighted score matching in this case, it's just the expected square distance of the scores. So here we have P, where this is our true data generating process, and P theta, which will be our model. And basically, we want to compute the divergence between those two things, which is the expectation of the square distance of the scores, where the scores is the Hilarion score, which is the gradient of density, right? Here we consider the weighted version. So we have a weighting function here on the beginning, which take a value of x and give us a matrix T on T. The case of WD, the case where W is just the identity, this is the original score matching. The problem is that we usually don't have access to this density, the density of the true data generating process, but you can do some trick and iteration by part. Usually you can rewrite the score matching as this term that depends on theta plus a constant that won't depend on theta. This leads to the natural estimator of this divergence, and this is the one that we will use as our loss function. So we use the estimator of the part of the divergence that depends on theta as our loss function, and that will be basically the main bulk of our method. So using this, replacing the loss function with this, hopefully will lead to a tractable and robust version of a post-Bayes inference. So in terms of tractability, first we'll focus about tractability and then we'll see if it's robust or not. I'll show that it's robust. So we'll compare this WSM base with standard base. And in the case that the likelihood is tractable, computing these posteriors is roughly as fast as on the standard base posterior, which is fine, which is nice. We are not increasing the computational cost of using this posterior. As I said, if we are working with intractable models, so we are not able to compute the normalization constant, then our or post-Bayesian method, it's faster to compute. This post-Bayesian posterior is faster to compute because we are able to deal this because we're working with the score function. But the case that we really care about, and the three examples that were before, is when you are able to compute the posterior closed form, which means that you are in this conjugate world. So you are assuming an exponential family model, and then you select a conjugate prior. In this setting, a standard base is available in closed form, and what about us? So the really nice things about score matching is that even though these loss functions look really weird and difficult in general, when you're working with a score exponential family, the score matching is just basically has this square form. It simplifies a lot, which means that the exponential of minus the loss function of the exponential of minus the score matching loss is just an exponential of minus something that is a square. And here it's super clear that if we select a square prior, you end up with a Gaussian posterior. What does it mean is that basically for every member of the exponential family, you have a conjugate prior, which is a Gaussian prior or a square prior. So this cannot be like a Gaussian all the time because sometimes you have like a theta that is always positive, so you can consider like a truncated Gaussian or something like that. So this is great because now, even in the case where the standard base is super fast and is the conjugate setting, we also are conjugate, which means we are as fast to compute as the standard base. So we are always more tractable than the standard base, but in all the settings in general. So what about robustness? Basically, here we have an example. This is what kind of like robustness we meant. We mean robust to fewer contaminations, which means that you have a bulk of data here that you really want to concentrate, and you have some epsilon contamination. So with epsilon probability, you will observe some contamination here at 10, but it could be any distribution that is far from the bulk of your data. So usually the standard base posterior will be influenced by these outliers, where in our case, we will concentrate under the true data identity process. How we show that this posterior is robust? Well, we use these ideas of influence function that was proposed first by Gaussian Basu, and then it was extended to this divergence-based posterior by Takuo. And it's basically when you assume your data come from like these pure contamination models, which is just one with probability epsilon, you observe C. And you compute a posterior given data observed by this contaminated model, contaminated model, and then you compare the posterior with respect of data that is just observed P, the true data identity process. If that distance is bounded for every epsilon, then you say your posterior is robust. So you have to select a distance with respect to this posterior. The distance that usually is used is just the supremum of all the thetas. So it's like a really coarse definition of robustness. But then if we use this definition of robustness, you can show that under some condition on the weighting function, these WSM-based posteriors are robust to outliers. I won't enter into a detail, but we can talk about this later if you're interested. So basically, what are the results? Like if you apply this weighted posterior or like weighted score matching posterior to the same examples of before, how it behaves. Here we have a Kalman filter where you basically track the same as before, and I'm just really tracking way better. And then same thing with Bayesian online changepoint detections, where you basically are more robust. So every time the bottom one is the standard base, the upper one is the WSM base, and we can see that the standard base kind of every time there is an outlier, you find a change point, where in our case, it's really following the correct change in the behavior. I'm doing time. Cool. So that was basically a way to do inference in a robust and tractable manner, right? But we can extend this to a regression setting as well. And in this case, I'm assuming Gaussian processes as a regression, but this can also be applied to Bayesian regression. It's kind of the same idea. Short introduction to Gaussian processes. Just a Gaussian process, just stochastic process, such that for every subset of observation X, the vector of evaluation f of x follows a Gaussian with prior mean m, with mean m and covariance k, which is given by the mean and covariance of the stochastic process. So we can use this as a base for Gaussian process regression. So basically, you assume your function follows a Gaussian, and people in practice select a Gaussian noise. This is your model now, a Gaussian noise, epsilon. And you can compute your posterior of your function will be given by your prior, in this case, be a Gaussian, time your likelihood, which again will be Gaussian because you assume a Gaussian noise. And therefore, the posterior is Gaussian again. It has this form, and as I showed before, it works really well. But then I already showed that this kind of like things, it breaks when you have outliers. So how we can extend this score matching base to this setting? So basically, we have to extend this score matching or weighted score matching for a regression setting. Now, the way to do it is just that rather than have an expectation only on X, you have a double expectation on X and Y, where X are your covariates, Y are your observation. And now your weights depends on both X and Y. You can do exactly the same tricks as before. This kind of like follow super naturally. It's not are the same trick as before. As I said, it's just like iteration by part, and then you end up with a similar loss function. But now rather than have p theta, you have p of your model, which is the likelihood of p of y given x. And if you do the same thing as before, so as I said, you use this score matching base as your learning rule. So now you have your posterior is proportional to exponential of minus some loss function, and the loss function is this weighted score matching. You, as we already talked and said, the posterior will be available in closed form because we are assuming a Gaussian model, which means exponential family. So our prior conjugate prior is Gaussian. So which would lead to a Gaussian posterior that has this form, right? So it's basically super similar as standard base, but now we have, again, this weighted function that is the one that will give us the robustness for all our methods. Yeah, I'll skip this. So overall, you can show and you can see that this score matching base and applied to GP, it's just straightforward. It's a straightforward extension, and you can see that in terms of how robust they are, if we compare against standard GP or other robust methods, we are always super competitive against the other methods, but in terms of time, we're way faster because we're able to compute the position closed form. Whereas if we consider like a more complicated method, you break the conjugacy and then you need to do some approximation, which leads to a loss in performance. And yeah, as I said, this kind of like framework is super flexible. Basically, every time you have something that is exponential family and you want to use conjugate posterior, you can use this weighted score matching framework to obtain robustness without increasing the computational cost. And every time you have a GP here, for example, you can apply it and you obtain a robust version of it. This is like a case on spatial temporal settings. And as in summary, just brief summary, we usually have standard-based inference, which is not robust. Not is either robust or scalable. It's not both because you have this trade-off between being misspecified and being able to compute this posterior, and using these post-Bayesian methods allow you to rectify this and getting both, getting robustness, but at the same time scalability. Yeah. So any question? Hopefully I took 20 minutes.
Perfect. Thank you for that. Excellent timing, Matias. We've got around 7 minutes for questions, so we can take questions until then before we move on to the next speaker. So are there any questions from the audience? Maybe I'll start us off while people are getting ready. Matias, I had an interesting question I was interested in whether or not the weighting function changes like computational difficulty. So are there, for example, choices of W that, I don't know, make MCMC converge kind of more quickly in the non-conjugate case, or
Oh,
is it sort of pretty independent?
this is a good question, to be honest. We haven't explored. We usually apply this to. We haven't used MCMC in this setting because we kind of like have been focusing on conjugate
Right,
posterior.
yeah.
But it does affect the computation because you have to compute this. Sorry, this term over here.
Mhm.
We usually assume like a diagonal weights, which leads to a super simple way to compute this term. But this posterior increases in the quadratic in the dimension of theta.
Yeah.
So it's not linear. So that's kind of like, yeah, I mean, that's kind of problematic.
Okay, I think we have a question from Josh. So
I
please.
Uh, Hi, yeah. Can you hear me?
Yeah.
yes.
Hi. Yeah, hi, Matias. It's super interesting. Thank you. Um, just a quick question. In my domain, I work in healthcare, and I have a load of time series,
Mm-hmm.
some of which have got kind of these severe outliers, and I've literally having problems trying to fit a GP onto them for this precise reason.
Mm-hmm.
But you get some that are relatively smooth, and you get a really nice GP fit just with like a vanilla setup.
Yeah.
So if I was to, so I guess the first question was, so I guess just treading back, so for these time series, I'd need potentially this robustness for some and the vanilla for another. Is there a disadvantage in using your robust version for all of them, or would you recommend kind of combining the vanilla and the robust versions in like a hierarchical model? Does that kind of make sense?
I don't get what do you mean by combine both? Like,
So yeah. So I guess my first question I, is there a disadvantage in using the robust loss for um for series that
on how
that have like a standard likelihood, if that
uh
makes sense?
Yeah, this is a good question. Obviously, when you are like going for a robust method, you always lose some efficiency. It's kind of
Yeah.
like we know that the Bayesian update is the most efficient one. But in practice, we tested that. We compare a lot against like data that don't have outlier, and the behavior it's pretty much similar. So we don't lose so much performance in terms of the absolute error.
Okay.
In practice, we haven't seen that. But yeah,
Uh,
obviously you could have like cases where they don't perform as good as the standard GP, which is kind of
Sure, sure. No, that makes absolute sense. And just as a quick follow-up, this just because I can't really visualize it in my head, but is it kind of straightforward to kind of hierarchically combine these robust GPs together? So kind of my current model is I have a GP for each time series, and then I like hierarchically combine them in a kind of meta GP. Is
good.
that is that straightforward with this robust loss, or is that complicate things?
This is a good question. I think it's something that we've tried to discuss with our people in the group. That
Okay.
I don't think it's straightforward to define hierarchical post-Bayesian methods. Uh,
Okay.
Maybe Jeremiah's could have like a more in-depth because I know he have like thought about this more.
Yeah, so you give up conditional probability with these methods. So
Right.
conditional probability is sort of the origin for the ease at which hierarchical Bayes springs into the world.
Yep.
And once you abandon conditional probabilities, you gain something, but you lose something. And what you
Yep.
lose is the ability to set up a simple hierarchy. So you would have to very carefully think about how to do it. And in fact, it's not clear to me at this point that there is a generic recipe that will allow you to define a hierarchical, generalized, or post-Bayesian strategy. It's not clear. It doesn't mean that doesn't exist, but if
Sure.
so, it hasn't been discovered yet. So
Okay.
if you figure it out, shoot me an email or write it down and send me the paper. I'll be very interested to read it. But
No,
yeah, it
no.
doesn't mean it's not applicable to your case. So Matthias showed us the Kalman filtering example. That's a very
Yep.
simple hierarchical model, but you do need to sort of think very carefully about what you're doing because you no longer deal with conditional probabilities. That's kind of the short version of it.
No, amazing. That makes absolute sense. No, to be honest, it is something I'd be interested in doing. So I would, I'll probably message you down the line. But thanks again for the talk. It was really interesting.
Okay, I think the timing is perfect for us to move on to the second speaker. So thank you so much, Matthias. We'll move on now to Harita's talk.
Yep. You see that? Yeah, cool. And you can hear me. Nice. Yeah, thank you for the introduction. So I'm going to talk about some applications of the Bayesian Nonparametric Learning and the Posterior Bootstrap that I've worked on over my PhD years. So a brief outline. So I'm going to give you the main idea of this framework, and then I'm going to talk about two kind of applications, each of which kind of I think highlight a different aspect of the framework, hopefully. So okay, so first of all, some very quick notation. So I'm going to be assuming I have IID data from the data generating process, which I denote as P star. And I have a model family that is indexed by some parameter of interest theta. Right. So I'm going to relax the first assumption later on in the talk, but for now I'm always assuming I have this IID observations. So if I could fit this non-parametric learning framework in one slide, it would be this one. So first of all, standard Bayesian inference, as we all know, it sets uncertainty directly on the parameter of interest theta via prior distribution, and then updates beliefs about theta conditional on the data. And it assumes that the model is correct, and we just care about this one parameter that perfectly describes the data generating process. Now, Bayesian nonparametric learning was introduced by a series of papers by Lydon and Edwin and co-authors. And the main idea lies in the fact that we see uncertainty as specifically not knowing P star exactly. So we don't see uncertainty as simply by not knowing theta, but we kind of view this all of our Bayesian uncertainty as a result of not having infinite data, in which case we would be able to recover P star exactly, but only having finite data and hence having uncertainty on P star. And of course, that's, just having listened to all these post-Bayes seminars in martingale posteriors and predictive inference, this is kind of like a notion that Edwin talked about quite a lot at the beginning of this chunk of series, where it's very similar to seeing uncertainty as uncertainty about all future data. So they're very well connected, and Edwin talked a lot about the connections to the Bayesian bootstrap. So hopefully you remember that. If not, you should go listen to his talk again. But for here, I'm going to kind of focus specifically on this non-parametric learning framework, where uncertainty about P star is modeled via some non-parametric prior, P, so I call P. So here I denote by blue everything that's like a prior or a posterior in the space of P star, and by red everything that's a prior or posterior on theta. So the whole concept is we start with a prior on P star, and we get a posterior. So again, that will be a non-parametric posterior. And what we want is to propagate this uncertainty about P star to theta, because in the end, we care about some parameter of interest. And the way we're going to do that is, of course, via some loss function. So here, the notion is very similar to generalized Bayes, where we define some loss in order to kind of capture which parameter we actually want to target, right? And in this case, crucially is we don't assume that the model is correct. So if theta indexes a model, which in general it doesn't really have to, but let's say in this case it indexes a model that we care about, then we don't assume that this model is correct. We just want to target the parameter that best describes the model, the data, where the best describes refers to some loss function. So we're going to define that explicitly. So in more detail, we're going to set a non-parametric prior, which is a Dirichlet process. So this is just a distribution over distributions, which is centered in some measure, prior centering measure f. So f is going to encode all our prior beliefs about P star. And then alpha, which is a concentration parameter, which will tell us how much we believe on f. And the nice thing about Dirichlet processes, apart from the fact that these two parameters are pretty interpretable, is that you get a really nice conjugate posterior. So now the posterior of P star conditioned on the data I have observed will be centered on this f prime, which will be just a linear combination of my prior and my empirical measure. So here, of course, if alpha equals 0, then we have this non-informative prior, whereas if alpha goes to infinity, then I only trust the prior and I don't put any weight on my data. So, okay, so I have a posterior on P star. Now I want to define some loss function on the space of my data and my parameter such that I can actually propagate uncertainty from P star to theta. So this loss function is actually going to define exactly what my target is. So again, we see that this is just a functional where, if I know P star exactly, then the parameter I'm targeting is just the minimizer of the expected loss under P star. But because I don't know P star, now I have this uncertainty which will propagate via this functional. So because I don't have P star, I have a whole posterior distribution over P star, and I can use the push forward measure of this functional given my posterior on P star to get a posterior on theta, which we denote by pi MPL here. So how do I actually sample from this posterior? So this is where the bootstrapping comes in. So to sample from this posterior, what people did in the posterior bootstrap and then later on in all this generalized bootstrap methods is essentially I need to sample from the Dirichlet process posterior. So that's again sampling on the space of P star. And then for each such sample, I get a parameter theta j that will be minimizing this expected loss. And this is the notion of randomized objective functions that was used in the first MPL paper, where essentially this is very alike the Bayesian bootstrap, where instead of kind of reweighting the data, you're essentially reweighting this objective function. So this becomes a randomized objective function because it's indexed by pj, which is now just a random variable where I have posterior beliefs over. And there's some links to the Bayesian bootstrap because if you think about what happens when alpha equals 0, so if I have a non-informative prior, what happens is I just get back what was called loss likelihood bootstrap. And if furthermore I choose my loss to be the negative log likelihood, I go back to Bayesian, to special case of the Bayesian bootstrap, which was also called weighted likelihood bootstrap by Newton and Raftery. So essentially what this means is if I have alpha equals 0 and I make an approximation of this DP sampling, because of course I can't really sample from this Dirichlet process exactly. So if I use the Dirichlet weight approximation of the DP, I basically get my first step accounting to sampling Dirichlet weights with parameters 1. And then my second step, just minimizing this empirical loss using these weights. Right? And that is if L is a generic loss, this is just loss likelihood bootstrap. If L is a negative log likelihood, then I get back weighted likelihood bootstrap, which is a version of Bayesian bootstrap in this case. So a bit of an illustration, again, before I move on to kind of applications of this. What this posterior bootstrap does is we draw some posterior samples from a Dirichlet process. So we start from posterior beliefs about P star, incorporating any uncertainty quantification and any probabilities I have for P star specifically. And then for each set sample, I basically map it to a posterior sample for theta based on a loss. Okay, so why would you want to do that? So there's a few ways to look at it. So first of all, this first paper motivated this MPL for a few different reasons. So one was this kind of relaxing this assumption that the model is well specified. So even conceptually, you start from a point where you don't want to assume a well specified model, but you want to kind of do this bootstrap operation to obtain some robustness with respect to model being misspecified. You can also target a functional of interest directly, which is not, for example, a parameter indexing a model. So, if you want to target the median directly, then you can define your loss accordingly. So you actually perform posterior inference for the median. Another kind of very nice property of this posterior bootstrap is, as it was shown in the paper by Edwin, one of the ones I cited earlier, is that it's really good for multimodal sampling. So actually, if you kind of perform this optimization step, and do like random restarts of this optimization step, you actually get really nice sampling properties to sample for multimodal posteriors, where standard Bayesian inference sampling would actually fail. And lastly, like if you can show nice consistency properties, and the nice thing here is that the choice of F, which was this prior centering measure in the Dirichlet process, does not affect these consistency properties, neither F nor where F has support on. So this kind of posterior bootstrap has been used quite a lot over the last few years. I'm going to talk about two specific applications I've worked on. And kind of my goal is to show in the first application, basically how you can choose the loss in a way to make it appropriate for specific problem settings. So similarly to generalized Bayes, if the way you choose your loss, he can give you nice properties for settings that have very specific requirements. So here we're going to talk about simulation-based inference. Now, in the second application, I focus more on the prior, and I wanted to kind of show that the fact that you can choose the prior within the Dirichlet process, which is kind of contrary to the Bayesian bootstrap, where you don't actually need to choose a prior at all, it can also help you kind of apply these methods to very specific settings by choosing the prior appropriately. So these are kind of the two lenses where you can kind of view this posterior bootstrap for this talk. So okay, so for the first application, it's a simulation-based inference setting. That was this work we did with Jeremiah, Thea, and effects. And here, basically, the setting is that we're in likelihood-free inference settings where we can sample independently from the model, but you don't have an analytical form of the likelihood. So these models, which are also called simulator models, generator models, they basically usually are very complicated models that try to explain some natural phenomena that are quite hard to capture with a mathematical model. And as a result, one, they usually don't have a likelihood, and second of all, they're very likely to be misspecified. So we just try to kind of apply this framework in this setting where you do want to target both of these issues at the same time. So a bit more specifically, just to remind you, notation, P theta index is the simulator model in this case. So mathematically, a simulator model means that in order to sample from P theta, you have to sample from a base measure U, which is usually something that's quite easy to sample from, and then map it through a simulator function. And again, we assume IID data, and we don't want to make the well-specified model assumption. Right, so what we did here is, as I said, is kind of choose this loss function within this MPL framework in a way that's suitable for this setting. So we use discrepancy-based loss functions and specifically this maximum mean discrepancy. So instead of expected loss under the data generating process, we have the maximum mean discrepancy between the model family and the MP star. And there's like two reasons why we chose this discrepancy. One is because as a frequentist estimator, this minimum MMD estimator, which is exactly the same as theta star L functional here, has been studied quite a lot in a frequentist sense, and it's been shown to have really nice robustness guarantees. So that was kind of choosing a loss in a way that making sure we have robustness to specification, while also using a framework that you don't assume that your model is correct. And then the second part is more computational because, of course, we're in the simulator-based setting, so we needed to choose a loss such that we don't need the likelihood. And the nice thing about the MMD is that it can be written as only as expectation of this reproducing kernel function. So MMD defines basically a distance by mapping probability measures to a reproducing kernel Hilbert space to basically the means of P and Q in the RKHS, and it can be approximated just by approximating this integral. So just by sampling from P and Q and approximating this integral. So it's suitable for simulator-based inference, and it already kind of inherits robustness properties of the MMD. And in this case, before I move on to the next application, just to kind of quickly show to you what kind of robustness I'm talking about. So this is kind of different notion than what Matias talked about. Here we looked at the generalization error of these posteriors based on the MMD. So under like a bounded kernel, basically we look at this expected MMD between the truth, the data generating process, and the estimated model essentially under expectation, both over a finite sample and expectation over the DP posterior. And of course, this is kind of lower bounded by this best case scenario, which is saying how close, sorry, my model family can get to P star. And the difference between these two is the generalization error. And here, the point is that one, looking at kind of the rate of this bound, which is just depending on n, and one is of the rate of 1 over square root of n, and secondly, the fact that it doesn't really depend on the prior at all, only through alpha. So these are the type of results we looked at. There's kind of some extensions you can get from this kind of generalization about, like, for example, linking to hubrid contamination models specifically, and like posterior consistency properties. Okay, so second application. So this was kind of like a quick application of like how you can choose L to make this very applicable for a specific setting. Here, apart from choosing L, we also look at how you can choose this non-parametric prior choice to make it very suitable for this measurement error model setting. And this was joint work with my PhD supervisor, Theo. So in the measurement error setting, we're in a regression setting where we care about performing Bayesian inference for the parameter theta that indexes regression function g theta, which explains the relationship between covariate x and outcome variable y. But x is only observed via noisy proxy w. So we have additive measurement error on x with zero mean. And here, of course, this type of error, this is also called errors in variables models in statistics. So maybe you've heard of it under that term. And the idea is that if you ignore the error on x, essentially you can get you can very easily show that the estimate of theta will be very biased. So if you care about actually estimating theta rather than just making predictions, this will have like a big effect on your inference outcomes. And so here we want to kind of perform inference for theta under a potentially misspecified distribution of n. So if I don't know actually how n is distributed, this is quite hard. And the main difficulty compared to everything I've told you so far is that now we don't even have observations from P star. So this assumption doesn't really hold anymore because P star is the true joint distribution of X and Y, but we're only observing from W and Y. Right, so the target parameter is the same as before, but now the idea here is that if I want to target specifically measurement error robustness, now the uncertainty on the data generating process comes from uncertainty of the conditional of X given W. So where by explicitly setting prior beliefs on the conditional distribution of X given W, essentially I'm saying I want to propagate uncertainty from how my true covariate relates to the observed covariate, and propagate that to my estimate of theta. So here we're doing kind of the same thing where you set a Dirichlet process prior, but now for each different WI, of course, this will define a different conditional distribution. So I will have to define a new Dirichlet process with a new centering measure F, in a way that makes sense and obeys the measurement error structure I have. And this is kind of the key point I wanted to mention about this work, which was like how you can actually specify this prior. And the first one is kind of to think about alpha. So here the parameter alpha has quite different role to what I had before. So here, if I set alpha equals 0, then you can easily see that it's like I'm setting all my weight of the posterior measure f prime to the observed covariate wi. So before alpha equals 0 was very non-informative. Now it's very informative because I'm actually saying, oh, I think there is no measurement error because I'm using my observed covariates essentially. Whereas if I take alpha equals 1, it's kind of like I'm, splitting the weight between the two, whereas alpha going to infinity is similar to before where I basically only trust my prior. But of course here my prior will have some dependency on WI as well because I'm setting a Dirichlet process on the conditional distribution. And to see that more explicitly, you can kind of think how I can actually set this prior centering measure in this case. And what I kind of want to take from this slide is more that you can basically define FWI in a way that obeys the structure of the measurement error you think you have. So a very kind of common differentiation between measurement error types is between what's called Bergson and classical models. And very kind of vaguely, the difference is that you basically make different dependency assumptions between X, W, and the measurement error N. So in one case, you basically assume that your observed covariate is independent of the measurement error, whereas in the classical case is the opposite. And this is actually quite important. So if you assume one and actually the other one holds, like your outcome will be both in frequencies and Bayesian methods will be quite biased. But here, if you know which type of error you think you might have, you basically can specify FWI accordingly. So just for a simple example, I'll give you the Bergson case, which is kind of simpler. Here we assume W is independent of N. So actually all we need to do is define some prior on N. So this will call this Fn. And then to sample for FWI, you essentially just sample from N and then add that additively to WI. So that would be like an example in practice, how that would look like. And then classical case is kind of the same, but you also need to specify some prior on the distribution of X, like the marginal, because it's independent. Cool. So I actually realized, so this was called applications, and I actually didn't really show you any experiments about these methods, but I do have some slides. If you're interested, we can do that during Q&A. But I was more like wanting to show you how this kind of bootstrap methods can actually be applied in more specific settings. There's kind of a lot more work I can think. So I didn't talk too much about the theory side of things. So I told you there are consistency results. I've actually been involved in some projects that are not quite out yet about proving more asymptotic normality results in more specific and general settings. There was also an application I've done on the decision-making setting with distribution robust optimization, where I just kind of tried one of these posteriors. So if you're interested in that, that's on archive. And something kind of more like on the limitation side. So I told you posterior bootstrap is parallelizable, which is really nice computationally. At the same time, this optimization step can be quite costly, and you have to do that a lot of times. And also, at least empirically, I've seen that this can also affect posterior coverage if your objective is not convex. So how you actually initialize optimization can actually have quite a big effect on that. So that's also something to keep in mind and maybe interesting to study more theoretically. Yeah, I think that's all. Thank you.
Fantastic. Thank you so much for that wonderful talk, Harita. Are there any questions from the audience? Okay, I'll also start us off again because I've got a huge list. I really like the second example where you actually constructed this kind of mixture of distributions. And one thing I was thinking about was whether or not you think that kind of idea could also be extended to like the robust kind of setting. Like I'm not sure if I can word it properly, but instead of choosing the loss function to kind of be outlier robust, could you like, pick the loss function to be something straightforward like the mean and actually like construct the prior to be robust outliers in a sense?
Hmm. Good question. I think, yeah, I guess the like this Bergson error case has like a hint to that in a way,
Mhm.
because what this does, if you think about, I guess, Fn just being a Gaussian with zero mean, it just does this thing where it just like inflates a bit your data essentially. Um, so I guess you could think of this as more like an outlier setting on your covariant, and that would give you some structure of that, but I don't really know how, like, yeah, how theoretically if you'd be able to show, that this would converge, like, kind of concentrate to the right place.
Yeah, it seems really hard. Yeah.
Yeah, it sounds quite hard to be able to guarantee something like that, but empirically, maybe it would help in some ways. Yeah, it's
Really
interesting
interesting.
to think about that. Yeah.
Perfect. Thank you. Do we have any other questions? Yes, I see Jeremiah says his head up.
So while we're on this slide, Harita, what can you actually prove here? So for these errors in the design of your measurement error,
Hmm.
how robust is this to different forms of wrong measurement errors, I guess, is my question. So it's clear, like when you have this very specific type of pollution, then this fixes it, which is nice. And
Yeah.
presumably is a setting people care about, otherwise it wouldn't have a name. But how much can you perturb this and still get something better? Or if you're in a slightly different setting, does this actually perform worse? Is there anything knowable about this, or is it just inherently sort of beyond the confines of our knowledge?
So do you mean more like if you had different structures of the error? So
Correct.
okay, so if you had like, so this is like, I forgot to say that this is all homoscedastic error, for example. So if you had heteroscedastic error, you would have to explicitly take that into account in your prior setting. I've only worked with these two types, and you can't get some guarantees that are, obviously under the assumptions that this is the error that's present, then you basically get something where it depends how you set F and how you scale it with alpha. So, if your F is really bad and your alpha puts a massive confidence on that, then yeah, you would be off. So you can't get everything for free, basically. You need to have some sort of good balance between how good your prior is and how much good you think it is, essentially.
So
But
So is this
yeah,
is this basically because sorry, maybe I misunderstand, but this is basically because what you're doing here is you're fixing a causal graph and you're fixing two different causal graphs in both of these settings,
yes.
and you can adjust the probabilistic model on the edge of the graph, or you can guard against mystification on the edge of the graph, but you cannot change the nature of the graph, which is kind of the problem you run into when you deploy these sort of post-Bayesian ideas in the setting of causal inference, that the main misspecification you actually worry about is usually the causal graph. Is that kind of what's happening here?
Yeah, I think that's a good Yeah, you said that quite nicely. Yeah, I think you can't really go with this, at least as it is, you can't really go beyond misspecified graph structure, or at least get guarantees. It might work in some case. Like I've tried it,
Sure.
it might work,
Yeah,
that's
yeah.
fine, but I don't think you can say that's, yeah. So that's why this actually in this setting, these dependency assumptions are quite crucial. But I think in at least a lot of applications I've read about, I mean, I don't know because I haven't like, worked with people that actually do this in practice, but it seems like you kind of know which type, you can know what type of error you have because it's very specific. If you think like it's coming from a faulty instrument, then we know that's high classical. So in some cases, I think that's okay to assume, but yeah, I don't know beyond that.
Great. Are there any other questions from the audience? Okay, well, if not, let's thank both of our speakers, Harita and Matias, and this marks the end of chapter 2, so thank you guys for ending it on such a high note. Thank you also to all the attendees for sticking with us so far. We'll now have a break for about a month and a half, so we're really looking forward to seeing all of you for chapter 3, which will be hosted by Pierre on Packbase. So see you guys around.